So I wanted to come back to this slide. I was re-reviewing, or I should say, I was reviewing my video, and I wanted to explain this a little bit better because I did a pretty crap job explaining this. So I'm gonna erase this, and I want to go back and really get into the details of this background single beam versus sample single beam, okay? Because I did not do a good job explaining that. And also I realized that I've got a bit of a mistake on my slides. So I'm going to label everything really carefully. We've got I0 and I, and I'll say that this is I0B for the background and IB for the background. And then we've got I0S for the sample and IS for the sample, okay? And so if we were to, so I've drawn a detector, the detector would be in the same position, right? Because it's the same instrument. And so if we were to look at what the single beam spectrum actually looks like, I wanted to go into that, okay? We can actually get a spectrum from each single beam, and it's going to be given as intensity versus wavelength, okay? Because each single beam spectrum is not going to be an absorbance spectrum. It's really going to be, if you think about it, it's an emission spectrum from the lamp itself, right? So I'll draw our little lamp right here, okay? So this is radiating out. Right, and particularly for the background single beam, since we're only going to get these scattering events, generally what we will see is a nice looking Boltzmann distribution, okay? So it's going to look something like this, because that's what the intensity of our light source would look like, all right? And so now over here, we've got the same light source, but now we've got some absorbing samples, okay? So this sample single beam spectra is still going to have this Boltzmann distribution of wavelengths, of intensities. However, if there are absorbing molecules in there, they're going to remove some of that intensity. So our sample single beam would actually look something like this with these features removed, okay? And so we still have this Boltzmann distribution, right? But there will be some specific frequencies that have been absorbed out of this intensity, all right? And so now if we think about this log ratio of ratios, then what will remain is the intensity of the background over the intensity of the sample, okay? Because everything, I0 background all the way up to this point will really be identical to the sample, with the exception, of course, of the intensities that have been absorbed, all right? So really now what this means is this absorbance is going to be the negative log of I sample, so the transmitted beam coming out of the sample over the transmitted beam coming out of the background, okay? So both of these two things will wash out because they're identical. And so now what our absorbance spectrum will look like, okay? So we'll have absorbance versus wavelength, right? And I already showed you in the other slides, let's see, right up here, right, where we take the log ratio of two identical single beam spectra, it's just going to be 0, and we'll have a flat line about the 0, right? So what that means is where our intensities are identical, so I'll put a 0 point here, we would see a 0 line, okay? And now where we see these features that have been removed, okay, because that's the, the intensity of the single beam over the background, and it's the negative log, these negative intensity features will appear as positive peaks. Okay? So that is a much better description than what I did previously. So I just wanted to take some time to walk you through that. Okay?